Hi, everyone. They told me they only have this microphone, so I guess I'm going to stick on this little podium. My name is Min, and I am a compiler plumber, work at Sci-Fi, and today we're going to talk about scheduling model. So, assuming I don't bore you 40 minutes later, at the end of this talk, you will learn that, first of all, what is scheduling model, and how do other part of LLVM use scheduling models, and what its connections with the actual hardware. And finally, I'm going to provide some food for thought about future direction of improvements. All right, so I'm going to, we fast forward to 40 minutes later. Now I'm going to go back in time and introduce the scheduling model by asking what it was invented for. So of course, according to the name, surprise, it was invented for instruction scheduling. So here I'm going to try to explain it in a slightly different directions and start to ask like what ingredient, what information does the instruction scheduler use from the scheduling model? So to answer that, we're going to the primary goals of instruction scheduler. So we can really boil down instruction scheduler into two tasks. First is to improve the instruction level parallelism, and the second one is to reduce the number of register spills. And we're not going to talk about the second one. And for the first one, I'm going to explain it with an example here. So on your left-hand side is a program in like a data dependency graph where the arrows means from the data producer to the data consumers. And what we really need to do here is to reduce the stalls. So what is stalls here? For instance, if you look at the left-hand side of this program, the load. So usually load, it will have long latency. So if we do absolutely nothing, then it will just fire the load and just run in, and the pipeline will do nothing else and waste a lot of cycles until it finishes. So what we want to do here is to have some not filter episodes, but filter instructions in between the load and the consumer, which is the add instruction here. So that is the first time. And if we go to here, this part of the program, we will also find that there are 3 instructions that can be independently scheduled. So although it can be because they don't have any dependency, but now we have a problem of if they are competing with the same resource. Now I'm going to be a little bit hand-waving and it will become more clear later, but you just think of the resource here is just some limited items. So we want to ask that if we want to schedule these 3 instructions where they're competing the same resource. And so if we go back to the original, like the load instruction, if we want to add the fill instructions, first of all, we want to know how wide is the gap. And the gap here is actually the latency, meaning how the total number of cycles is going to take to execute this instruction. So that is latency. And when it comes to these 3 instructions, we're asking whether they're competing with the same resource. So let's just assume that the multiplication and the subtraction instructions are using a different resource. One is IEX, ALU0 and ALU1. With this information, we know that we can schedule them at the same time because they're not going to competing with the same resource. On the other hand, if the multiplications they're using, of course they're using the same resource, and the second multiplication, it needs to wait for some time before it can grab the resource and start to use it. And the time it needs to wait here is called the occupancies. So latency, the resource, and occupancy. These 3 are the primary 3 ingredients the instruction scheduler needs from the scheduling model. So for instance, the left-hand side table, it can be one of the simplest scheduling model. It's just a huge tables with instructions and what are their latency, resources, and occupancy they use. This is probably what the scheduling model kind of looks like. And that would be a good segue to see what the actual scheduling model. Let's start from the legacy one. It's called the itinerary model. Unfortunately, we're not using that anymore, but the ideas of itinerary model is it will model instruction with a multiple instruction stage. So for each instruction stage, it will tell you, well, the occupancy, how many cycles it spent on this stage, and what resource it used on this stage. And finally, of course, the entire, all the stage, the time it takes will be the latency. Now, we can really see the inspirations of processor pipeline model, from the previous pages by splitting into multiple instruction stages. So this diagram is what I copied from the traditional textbook model about processor pipelining. So if we apply our three key ingredients in here, the latency is, of course, how the total cycle is executed throughout each processor stage. The occupancy, that's, for instance, the instruction 0. The occupancy means the amount of time is spent on the execution stage. Here, we really only care about execution stage, and we don't really care about other processor front end in scheduling models. And so this is occupancy. And it will become much more interesting if we put superscatter into this picture. So superscatter is basically that we are going to replicate the pipeline we see in the previous page into multiple units so that they can execute at the same time. So here, this unit, we usually call it execution pipe. And as we say, we replicate the same pipeline and so that they can execute at the same time. Same for the occupancy, it has the exactly same meaning. So with this mental model, it's actually a lot easier to explain resource, because now resource just means which pipe, execution pipe you can run on. And as you can see, some instruction can only run on some of the pipe, like instruction 0 can only run on IEX 0, but for instance, instruction 2, it can run on either the IEX 0 or IEX 1. So that is the concept of like execution resource. Now we have the intuitions of how it maps to the hardware, and we know what the instruction scheduler wants. Now it comes to the current generations of scheduling model. It has a name of instruction scheduling models, but I will just call it scheduling models. Instead of splitting instruction into different stages, it starts with an individual instruction and focuses on the operands. So it split the operand into the one that writes and the one that reads. For the operand that writes, it will assign a token and use that token as the key and map to an entity called write-res. So this entity, write-res, will contain the three ingredients we mentioned before. The resource it used, the latency, and the occupancy. The occupancy is represented by two different fields, acquire as cycles and release as cycle. We're going into details of that. But basically, this write-res is what constitutes the scheduling model. And to see this in actions, when we're defining instruction, we will attach the token, which is the write ILU here, for the instruction. And usually on the different file, on the scheduling model file, we will write the write-res with this syntax, which contains, of course, first the resource here, which we use pipe AB in this example, and occupancy here. And finally, we also have the latency. So let's start, talk about the details of the resource first. So this pipe AB is declared by the product resource. So for instance, here we declare product resource pipe A and pipe B. And sometimes we want to say, hey, this instruction can execute on either or pipe A or pipe B. In this case, we're using the product res group. That's how comes the pipe AB. And sometimes like some instruction can only use one of the resource. And if an instruction, and if an instruction want more like both resource at the same time, then it will just post both resource in the write-res records. Now we learned the resource it used is strongly connected with the occupancy. So the way we express occupancy is through the acquire as cycles and release as cycle. This is like two arrays which has the same amount of element as the number of resources you use. For instance, here we use two different kind of resources, so you have two elements on these two. So the blue text represented the start of the cycle, it acquired pipe B, and the end of the cycle, it released pipe B. So same goes to the green one, which is the second element of both arrays. It started acquired on cycle 0 and releases at cycle 33. So the cycle 1 will be the occupancy it implied on pipe B, and 33 will be the occupancy it implied on IDEF resource. So this is how we express occupancy. And this is also a real example to show that, for instance, in this case, we roughly have the same latency, 34 cycles, as the highest occupancy. So if this happens, it usually represents an on-pipeline instruction. I know it's 2025, it's hard to imagine some instructions are not pipeline, but it's actually pretty common for division instruction like this. Complicated instruction, it doesn't worth it to pipeline it. So this is how we represent on-pipeline instructions. Now, you probably already saw the hints here that the acquired cycle can actually be non-zero. We don't necessarily need to acquire from cycle 0. So for this one, I would like to point it to Francisco's really good LLVM 2023 talks about when we need acquire cycle not equal to 0. But overall, this is how we express occupancy. Now, if we put everything together with the right res, we can know that when we're scheduling the load instruction in the earlier example, because we know the latency, we know that we need to push the add instruction that consume the result later rather than earlier. Otherwise, the add result will be there and just waiting for the results. Sorry, the add instruction will be there just waiting for the result when it's not ready. And here we're trying to prevent something called data hazards. And with the proc resource as well as the occupancies, we know that although these 3 instructions, they can schedule together, but they, for instance, the 2 multiplication instructions, they're competing with the same resource, so that the second one needs to be a little bit later. On the other hand, the mul and sub, they're not competing with the same resource, so they can be scheduled together. What it tries to prevent is so-called the structural hazard. So these 2, data hazard and structural hazard, and all these is what the scheduler is trying to prevent, and so that it just shuffle the instruction accordingly. But there is, of course, another way to prevent like this kind of hazard in the hardware, and that is the auto-order execution. What it means is that the same pipe we saw earlier, but now we slap a buffer in front of them. So the instruction will be first dispatched into the buffer, and we will just stay in the buffer until its hazard got resolved before it actually issues and starts to execute it into the pipe. And to give you an idea of how the auto-order execution works, I would like to introduce tools here, the LLVM MCA. So LLVM MCA is yet another tool that uses the scheduling model, but instead of using that to shuffle instruction around, it tries to simulate what the actual CPUs or processor do. So here, it shows the cycle, and it will give you a timeline. And I show the legends of the symbols on the timeline. What's more important is the D means dispatch, and both the lowercase e and uppercase e means execution. So, for instance, in this example, we saw that with auto-order instruction, the last multiplication instruction actually started to execute before the second instruction even started running. And that is because there are a data dependency between the first instruction and the second instruction, but there is none on the third instruction. So the third instruction can, of course, just start to execute it. It doesn't need to wait. So here is how it resolve, how the hardware resolve data hazard. For the structural hazard, we're going to use an example here where there are 3 multiplication instructions, and it can only execute on one of the pipe, while the add instruction can execute on arbitrary pipe. the same phenomenon we also hear. The same phenomenon we also see here. The last instruction, the last add instruction, actually start to execute before the last, the third instruction start to run. That is because they are not competing with the same resource. Like the multiplication depends on only one of them, but the add can be freely executed on any of the pi. That is how the real processor resolve structural hazard. Okay, I think I need to click it on the side of the laptop. Okay, cool. And now we learn like how the outer order execution works, right? Of course, the scheduling models, of course, need to account for that. How we represent it, or the diagram we saw previously is a previous page, is also known as the unified reservation station. That all pipes are sharing the same buffer. In this case, we're using the micro-opt buffer size to represent the quantity, the size of the buffer. And at the same time, we need to set the buffer size equal to -1 as a hint to individual pipe. Another style, like we have unified reservation stations. So of course we have decoupled reservation stations. In this case, each pipe has its own buffer, and the quantity of that is specified using buffer size attributes. Another variant of this decoupled reservation station is, more than one pipe might share the same buffer. And the reason the hardware wants to do this is it actually can give you more freedom when you resolve the structural hazard, because now an instruction can stay in one buffer and it can freely go to either of the pipe instead of just stuck in one buffer of the specific pipe and just stay there in case the hardware scheduler did something wrong. So it gives you more freedom. Actually, we can think of the unified reservation station as the most generic ways. If we generalize the decoupled reservation station in this case, it will just become the unified reservation station. So in theory, the unified reservation station has the highest flexibility. Now we talk about the outer order execution, and the scheduling model, of course, needs to account for in order core. In this case, the first kind of in order core, of course, just set the buffer equal to 0 because it just doesn't have buffer. In this case, if there's an instruction still executing in the pipe, the following instruction will just be refused to dispatch in this pipe. Now, there's a really special kind of in order core, is that we actually set the buffer size equal to 0. We will see a little bit more concrete example later, but the idea is that the following instruction won't be refused to dispatch right away. It will just stay in the really, really tiny buffer as like the staging area. So what are the difference? The difference is that we can actually see from using MCA again. For buffer size equal to 0, we can see that the second instruction, the second division instruction, will just not be able to dispatch until the first instruction finishes its execution. On the other hand, if we set a buffer size equal to 1, it will still dispatch right away, but then it will just stall in the buffer for a really, really long time. So that is the difference. But conceptually, both of them are still in order execution. There's no way the hardware can shuffle them around. So you might wonder if in the hardware they're basically the same, why do we need to separate them into two different categories, the 0 and 1 category? And that brings us to the next section, is that although the scheduling models try to provide the same amount of information to the user, in this case, the LLVM MC and the instruction scheduler, they actually have a different way to perceive this scheduling model. So the biggest difference we're going to see here is the outer order buffer size, the quantity of the size. For LLVM MCA, all the diagram we saw earlier are how the hardware looks like, and MCA basically had the same interpretations as the hardware as we introduced earlier. But for machine scheduler, It doesn't use the quantity at all. It doesn't use the buffer size at all. And the reason is that, well, we cannot predict how the hardware scheduler, schedule the instruction in runtimes, right? So it's nearly impossible for the machine schedulers, which is the compiler, to predict that. So it just not use the buffer size at all. Of course, it is possible for, in real execution, for instruction to overflow the buffer. Here's a formula that specifies conditions, where if you just keep pumping the instruction into a specific pipe, and you have a long execution, long running instruction like the K here, it is possible to overflow that. But I guess people just think that it rarely happens, so it's not really worth the efforts to model this kind of overflow incidents. On the other hand, the in-order scheduling is extremely hands-on. It will try to predict the stalling during the compile time because it can. Because what it predicts is basically how the actual execution looks like. In fact, the diagram we saw earlier on the right-hand side is roughly the same as the internal data structure the machine scheduler uses to do the in-order schedulings. And it is so much that if there's a hazard, like the data hazard and structure hazard we mentioned earlier, if there's a hazard, it will even refuse to consider that into the core scheduling algorithm. So what does that mean? And this is another internal data structure that used by the machine scheduler. So on the right-hand side is the most right-hand side is the core scheduling algorithm. All the fun things happens here. But it will only see the instruction in the available queue. It will not see any other instruction in other places. And how the instruction into the available queue is from the pending queue. The instruction will become legal to, when it becomes legal to schedule, like all the predecessor or successor has been scheduled, it will go into pending queue. And the transition between pending queue and the available queue is the hazard. So for an order course, it will check that whether there's a hazard, the data hazard, and the structural hazard. If there is a hazard for an instruction, then it will not go to the available queue. But on the other hand, as we shown here, it doesn't do that check for out of order. For out of order, it basically do zero check, and it will just, the instruction will just migrate from pending queues to available queue. That means the machine scheduler is basically more optimistic on the out of order code because it just trusts the hardware will do the right things. And it also means that there is basically no resistance from migrating from pending queues to available queue. And I want to add another thing into this mix is the buffer size equal to 0. Because in this case, buffer size equal to 0, in the hardware is still in order. But in this case, it will not do the hazard check as well. So that means it's an in order core, but it was scheduled out of orderly. That means also have basically no resistance from pending queue to the available queue. So what does this mean is that it has a really duality or awkward situation is that conceptually, machine scheduler is a little bit too optimistic and expecting some capability in the hardware that never exists. That, because it doesn't check for the hazard, but in the real hardware, it will just stall on dispatch. So for what is worth is that when it schedule buffer size equal to 1 instruction, it still check for data hazard, but is only used as more like a cost model or like a cost instead of like a showstopper that will stop it from migrating to available queue. But on the other hand, sometimes this can be a useful tool because for buffer size equal to 0, it will just not consider any instruction if there's a hazard. But we've seen cases that, for instance, an instruction has a hazard of, it will stall for 1 cycle, so it will not be considered in the scheduling algorithm. But what it doesn't know is that it will reduce the register pressure by a lot. And if it's able to reduce the register pressure, it will prevent a register spilling that might bring 10 cycles of penalty. So although it only stole 1 cycle in the pipeline, but actually it can improve the performance by 10 cycles. The scheduler doesn't know that. for in-order code. It doesn't know this kind of things because it would just say, no, 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 you have stalled for 1 cycle, you cannot go into available queue, so you will never see that it can actually reduce 10 cycles. So I hope in the past few slides I have convinced you that what really matters is not the scheduling models, it's about how it uses, how it perceives and how it interprets it. And that is the point of studying or using scheduling models. And at the same picture, we're discussing like instruction scheduling and the LLVM MCA. These are the two users. In the final section, I'm going to ask the questions: can we use that in more places? What other places are using, and can we use that in more places? So right now, here are several other users of the scheduling model. I would like to start with the machine trace metrics. This is definitely an underappreciated, underutilized utility. It's pretty awesome because it actually tries to give you the traces, possible traces, potentially using the BPI, the block probability informations, and it will give you the latency and the throughput of these traces. Unfortunately, as I say, it's underutilized, and right now it's only used by A, the machine combiner, and B, the early if conversions. And both of them only use it primarily on the latency information. For instance, the machine combiner use that to reduce the critical path, and the if conversion use that to see whether it's worthwhile to turn branches into predicate instruction. There's, of course, the machine pipeliner that use all the informations and is doing the software pipeline. So it will be helpful if the critical path of the loop body exceeds the size of the loop, so you might want to overlap the instruction from different iterations. Now, I want to throw in open questions here to explore the possibility of using scheduling model for the TTI cost model. So what is TTI cost model? TTI stands for Target Transform Info. A supply cost of individual LLVM IR instruction to multiple users, like most notably the vectorizers. And what it gives you is throughput, latency, code size, and a weighted combination of latency and code size. And as I highlight here, since it's supply, throughput, and latency, it will be interesting if this information, which is right now just implemented by individual target, and supplied with a scheduling model instead. And the pros and cons of this is that there's a huge gap between the scheduling models and the TTI cost model. Because, well, the advantage of this unification is, of course, now you only have one place, a single source of truth, and you only need to update in one place instead of two places. But the challenge of that is, the biggest one is there's just a huge difference between LLVM IR instruction and machine instruction. So in order to have a faithful estimation, you effectively need to do some simple ICEL on the LLVM IR instruction in order to use the scheduling model to give you, let's say, latency or throughput. And another thing is just, do we really need it now? Because let's say, in most cases, we don't really care about the cost of simple instruction, and we probably only cares about for complex instruction. And maybe there's only a handful of complex instruction, and it is sufficient to use if-else statement to give the cost of that. So these are the pros and cons, and these are the open questions I want to throw out here. And other potential uses including, because software pipeline is hard, so maybe we can use a scheduling model to guide the unrolling so that it will unroll in a way that it will improve the scheduling. There's only, so previously we mentioned that there's a different interpretations between the machine schedulers and the LLVM MCA. So it would be cool if right after the scheduling, we actually use MCA, which has a different interpretation, to validate the scheduling results. And third one is actually a funny one, but I have to mention. So the instruction scheduler right now in LLVM, both scheduler, is using a greedy fashion. That means what the order of the ICEL patterns matters because they apply in order. Right now, we order these patterns with some heuristic but not latency. And there's comments in the TableGen backends that generate an ICell saying that, hey, we might can use latency to order these patterns. And it's notably to mention that this comments was written by no other but Chris himself over 20 years ago. So this idea has been floating around for 20 years, and I thought it's funny to mention here. It is still possible, but I just don't know how much work and whether it's worth it. So in the past 40 minutes-ish, you learn what exactly is scheduling models, what it provides, and most important of all, the key about the scheduling model is not about the model itself. The model itself is just a bunch of numbers. Like you can even use a JSON file and it will just work. What it matters is how they use, how it got interpreted. That's what we should focus on. And finally, I provide some food for thought of future improvement, future directions of scheduling models. So with that, I'm happy to take questions.
Thank you.
So I noticed in the table gen you can put multiple pipes for one instruction, but has there ever been a situation where one pipe, the instruction takes longer than in another pipe, and are you able to represent that in table gen as well?
Yeah, so you specify different cycles each pipe needs.
Right.
Yes. Yeah, I think early example also shows different cycles for different pipes. Yes.
All right. Yeah. Thank you.
Yeah.
Thanks a lot for a nice talk. And perhaps I missed it, but you talked about write-REST, right? This token.
Yes.
What about read side of things? I'm not
Yeah. So good question. I was debating with myself what should I put in. I have a really long agenda list of what I want to talk about. So the read one is primarily for pipeline bypassing. Sorry, pipeline bypassing. So you can say that this write the scan write token will bypass to this read token by how many cycles? Then that's how you express pipeline bypass. Yeah. It's also known as read advance. Well, in TableGen it's read advance, but it's easier to understand bypass.
We still have a lot of time for questions.
Oh, I was speaking too fast. I tried to slow down, but
It was a great presentation.
thank you.